So in this video, we will talk about methods of estimation, right? So um, how this will show us how we will be able to estimate the parameters of a distribution. And here, we are not talking about the theoretical aspects. We are talking about the case where we have a data set. We want to fit a distribution of today's data. Now, to do so, it means that you need to be able to fit a particular distribution, so maybe a normal distribution, a geometric distribution, a Poisson distribution, exponential, and so forth. And but you will say that you have fitted that distribution if you are able to compute an estimate of the parameters. So, for example, in a course like 333, which is statistical methods. Students are introduced to various types of estimation techniques. Um, Chiefly among them is the methods of maximum likelihood estimation, but of course there's method of moment, there's probability weighted moments, elemental percentile methods, and what have you. Least squares is also an estimation technique, and so forth. So just to mention a few. Okay. So here, our focus is to be able to do this in R. Okay. Now, how do you go about this? Well, there are sometimes inbuilt functions to do some of these things. However, it is not always the case that you will be able to find a function that will do a particular thing for you. Okay, so how do I explain this? Well, um, if you want to fit a distribution and the distribution is widely known, okay, and that distribution has been worked on by some people in R, or let's say in other um, programming language, then you can sometimes import it and so forth. But there are instances where, let's say you have a distribution, and let's say you discretize the distribution. Well, what do I mean by this? So I may have a continuous distribution which has maybe some very nice properties, but my data that I have is discrete, and I believe that, okay, if I am able to discretize it, in other words, if I'm able to make this continuous distribution a discrete distribution, it's going to, I mean, fit or provide a better fit for my model, for my data, I should say. Then if I do so, you may not really find a standard function in R that will do such a thing for you. Okay, so I will share one of the thesis one of my students who worked under me did in his master's, which was about the generalized Pareto distribution and its discretization. So I'll share the paper with you. It's been published so that you can have a look at it and see what I'm talking about now in practice. Okay. So how do we go about maximum likelihood? So just a quick review. So usually for maximum likelihood distribution concept, you have an x, which is a random variable, and this random variable may have a distribution. Okay. So for a start, let me say this function has, let's say, it has a geometric distribution. So it has a geometric distribution with parameter theta. Remember that for a geometric distribution, it's the you state what your function, okay, all right. So the if theta is has a geometric distribution like that, the probability that x is equal to small x will be equal to theta 1 minus theta, okay, x minus 1, where x will take on 1, 2, 3, and so forth. Remember that in a geometric distribution, it's or the underlying experiment is what? A Bernoulli. So we perform a Bernoulli. What is a Bernoulli distribution? Well, it's a distribution which will have what? Has one or two possible outcomes, right? Okay. So it may be that, let's say we have that an example could be that you are drilling a well, let's say Cape 3 Point, they are drilling for oil. So you drill until you hit an oil. So every meter that you drill, you may hit oil or you may not. So that's an experiment consisting of two possible outcomes. Okay. Now, if we do this until we get we strike an oil or oil, then it means what? This is what a geometric distribution, unlike a binomial, which will um, give us or which we will specify a certain number of a certain number of trials that we have to do. Okay. Okay. So here we can um, we can state our likelihood function. Okay. So for maximum likelihood, you need the likelihood function. So the likelihood function, okay, which we call L theta based on our data X, will be equal to what? It's the product of if our sample size is n. Okay, then is the product of the probability, right? Your probability function. In this case, a probability mass function. Okay, so our P, okay, where X will be will take on X side. Okay, so like that. Now, if in this case, what is our so in this case we have so it will be the product, okay, of what? Theta 1 minus theta x minus I. Okay. Now what it means is that this will give us um, theta n 1 minus theta, okay, and then we have what? Sigma x, sigma x. So this will be sigma x minus, and this will be n, right? Okay. Now, what it means is that I can also write this as theta n 1 minus theta theta. Okay, and then this will be n x bar minus 1, n x bar minus 1. Okay, because n times if I take x bar out, sorry, n out, then this one will become what? Sigma x over n, which is x bar. Okay, so we can write it like that. Okay. if we do that, okay, if we do that, we're going to get um, our log likelihood is okay. So this will be equal to, then we have what, n log theta, okay, plus n x bar minus 1 log 1 minus theta, theta. So that this is our log likelihood and then the likelihood. Okay. So that's basically how you find, and in your, let's say 333, if you want to find theta, you are going to find what the partial derivative of what L or L the likelihood or the log likelihood. Usually we use the log likelihood because any of the estimates, okay, that will maximize. Here we try to maximize the likelihood. So that will maximize the likelihood function. We will also maximize what the log likelihood. So that's the concept we use. Of course, we can give other examples like let's say the if we have let's say if also Poisson distribution. So for the Poisson distribution, Poisson, so the Poisson distribution, okay, that we will x this Poisson with let's say the parameter lambda, then we have that the probability that x is equal to x will be equal to e to the power lambda to x, then x factorial. Of course, x starts from 0, 1, 2, and so forth. Okay. Now, so with this, just like we went through the other one, um, we can find our likelihood. So the likelihood function, the likelihood function L lambda of x bar will be what? Will be the product. Will be the product moving from 1 to n e to the power lambda to the power x factorial. Now, which means that I mean, if we find out the product, of course, this we can find also our likelihood and so forth. Okay. So that's the concept we use. Okay. So this will be e to the power negative n lambda, and then you have lambda e of x, lambda sigma x. Of course, x sigma should move from a 1 to n. Okay, your sample size. Okay, so this is n, and then we have what pi x factorial. Of course, pi also move from 1 to n. So that's the complete specification that I was saying. Okay. So of course we can find our lambda x prime, which is that we find the log. So if we find the log, we'll have negative n lambda, okay, plus, of course, uh, yeah, log. Okay, this should come first. Sigma xi, okay, so this is I, sigma xi log lambda, and then we have what? Negative, of, because this is 1 over that, so we have log pi, so that becomes the sum. Okay, so but that part, okay, so log pi I and x prime is not really part. Okay, why would I say? Because remember that you are going to, if, as I said, if you are doing 333, you are going to find what? Lambda delta L over delta lambda. So because this one does not involve lambda, because certainly it's just pi I from 1 to n, right? Okay, x prime. So there's no lambda attached to this part of it. So if I differentiate, this is like a constant with respect to lambda. So it is not part of our score function. So our score function for this um, the Poisson distribution is only this part. Okay, this doesn't really contribute to it. So when we go to R and we are finding our own function to do this estimation, we will ignore this part because it won't be part. So from this review, we can now go to R to be able to find or start doing our maximum likelihood estimation and then other. Okay, so in R, there are various ways in which we can do a maximum likelihood estimation. So first of all, we will try and use the inbuilt function for doing maximum likelihood. Now, for us to be able to use it, you need to take mass. Remember the package mass. Okay. So in package mass, there's a function fit dist R. So let's look at the help files for fit dist R. So what does it say? It says it's what? It's a maximum likelihood fitting of univariate distributions. So maximum likelihood fitting of univariate distribution, allowing parameters to be held fixed if desired. Okay, so essentially this function fit x this need x, and x is what? A numeric vector of length at least 1 containing only finite values. So these are the data. Okay, then another argument is dense fan. So what is dense fan? Dense fan is a distribution function. So there are several distributions that you can use or you can fit. For example, a beta, for example, a Cauchy, a chi-squared, an exponential, a gamma, geometric, log normal, normal, logistics, negative binomial, normal, Poisson, T, Weibull. Okay, these are all recognized. Okay, now remember that you see for maximum likelihood, this is the interface between the theoretical aspect and the practical aspect. Remember in like a 333, when we say find the maximum likelihood estimator, you do you form your likelihood, you find your log likelihood, you differentiate with respect to the parameters you want to estimate, you set your function to 0, then you find your whatever. So your estimate, for example, for the normal distribution, you have mean for the mu, and then also the 1 over n sigma as what sigma of the square deviation as well as your variance. In practice, things does not work like that. So, for example, when we give you a data set, you don't just find a mean and then use it as an estimate for the mean of the normal distribution. No. Okay. What happens is that you have a data set, okay? So you have to provide a starting value for the maximum likelihood. So it's like an iteration, okay? Now, in this fit.dist, you can provide or you can leave it. If you leave it, it will start from a point. Okay, usually if you are doing this in practice, the easiest way to do it is that you start with the moment estimators because those are easy to find. Okay, so if it is normal distribution, the moment estimator will be the mean. So I just use the mean as a starting point for the mean, and maybe the variance as the starting point for the variance. Okay, that's it. And then the function will be iterated until it gets closer to the unknown population mean. So, for example, we say that if the difference between the unknown population mean and is less than maybe 0.0001, you stop the iteration. Sometimes it can be a number of iterations. So when you are doing this, it will iterate maybe 1,000 times or 10,000 times. If the solution is not found, it will curtail it there. And then what the value of your estimator at that point is chosen as the maximum likelihood estimator. So that's in practice how maximum likelihood is done. So you realize that when we start doing our own functions to do so, to find maximum likelihood, we will return to what we called optimization. Okay, so remember in your mathematics, you, for example, do bisection method, you do the Newton-Raphson's method. Okay, so all those things are ways of finding the zeros of a function. Okay, the secant methods and so forth. There are so many of them, Brent and so forth. So that's the principle. Remember that the maximum likelihood estimation in practice start from where you set your value to be zero. So where you set your functional value to be zero. So we find the differential, we set it to zero, and then you are now iterating that function until you get the zero. It's not always the case that you get exactly zero in practice. So, the theoretical aspect is different from when you have, practical situation where you have to deal with. And maximum likelihood may, sometimes you may not even have an explicit expression for the differential, okay, let alone be able to find the zeros of it. So that's what you should bear in mind. Okay, now so for this distribution, we can easily find it by either stating it. We can also get additional parameters. Okay, remember that I said here it's you are doing an optimization. So to do so, we use what optim. So if you have to add, when we are doing our own, or we are finding our own ways of finding a maximum, like you're writing a function to find the maximum, like you will either use optim or yeah, or constrain optim. In cases where your parameters are what constrained, you use cons optim and so forth. So in this case, you combine what your mathematical studies on, let's say, finding zeros of a function as against your ideas in estimation, which is this. Okay, so let's look at some examples. Okay, so an example, let's say we get we have a sample of values. So let me take generate observations from the exponential distribution, which ESP. Sorry, it should be RESP, right? RESP. Okay. So this function needs what? The sample size. So let me take a sample size of, let's say, 20. And then the rate, let me say a rate of 0.5, meaning my mean is 2, right? And so forth. Okay. So let's look at this. So E dot sp is now an exponential function. I can plot it, okay, maybe a histogram of it, okay, and this will give you something like that. So if I fit a curve to it, a density curve, you realize that this decay is more or less exponential, right? Okay. So, and usually we do per ma. One. So what there are so many spaces over here. Also, I don't want to see this histogram of ES over there. So I say main is empty, and also I reduce the spaces around this area, and then at the top area. So that's the essence of this um, code. And now you look at it, it looks like this. Okay, so um, so this one, my slab may be, let's say, time. Okay, so slab instead of maybe time. Maybe this is the time, it's service time of some customers at a bank or something. So it looks like this. Most people, if it's in minutes, most people are served between 0 to 2 minutes and so forth. So this is our data. Okay. Now, even though I know the parameter, this is what we term as simulation, right? In statistics. So I know the exact parameter value, and then now I'm going to use. So if, for example, I need to test some estimation methods. This is what you do. So you simulate observations, and we are going to go through this to let you know that as we increase the sample size, our parameter value or the estimate of our parameter will get closer to what? To the unknown, in this case, the known parameter. So you use your estimator to estimate the parameter. And as we increase the sample size, you realize that the estimate will get closer to the parameter. So under simulation condition, we know what we want. Okay, if it is a parameter, we know exactly what the parameter is, and then we generate observations, and then we try to see how close our estimate is to the parameter. Okay, now, so if I have two estimation techniques, maximum likelihood, maybe method of moments, and also least squares, no, I can do this over and over and over and over again, usually over 1,000. And then I check how close they are to it. So the bias and the mean square error that you did in your, like, in a course like 333, you find the bias as well, the expected value of your estimator minus what? The parameter. Okay, so now I know my parameter. Okay, my expected value is the mean. So if I have there's so many 1,000 repetitions, I can find the mean of this estimator, and then I can now subtract my parameter. In this case, my parameter is 2 if I'm interested in the mean, or 0.5 if I'm interested in the rate. Okay, I subtract it from the mean, and that becomes my bias. If it is negative, then it means I have a negative bias. If it is positive, positive bias. If it is 0, it means it is what? It is exactly equal to the parameter. And also, I can find my mean square error as what? The average of the square deviations. So, I mean, in even though we have formulas for mean square error and standard errors, as I said, it's not always the case that you can find that mean square error. So sometimes we have to use empirical means. And to use empirical means, that's what we do in that aspect. So whatever you do, that theory, you can now translate it into some programming aspect and be able to find it practical. What about when we have in practice a data set? When we have a data set in practice and you want to find maximum likelihood, then you go through it like that. But remember that in practice, we don't know what the parameters are. So you cannot just go on and find mean square or bias when you don't have it. The only thing you can do is to now do replications. And in that case, you go to the bootstrap world. Okay, so bootstrapping is just like resampling. So it's just resampling from the same data. So remember, in the simulation aspect that I've done, which we call it Monte Carlo simulation. So there's a difference between Monte Carlo simulation. We call something Monte Carlo. So Monte Carlo simulation. Um, yeah, Monte. And remember, Monte Carlo is so Monte Carlo simulation. Okay, and then we have the bootstrap. Bootstrap. So the principle is simple. It says that it's like you are you are drowning and you are using your bootstrap. What we would say late. Okay, bootstrap. So in statistics, when we say bootstrapping, it means resampling. Okay, so if I want to find, let's say, the um, the standard error of let's say correlation. Okay, then I have a data set. So maybe I selected 10 students. I measured your height and your weight, and I want to now find I found the correlation. The correlation is 0.6, which means um, as your weight increases, we expect your height to increase, right? But of course, marginally. Now, in statistics, you cannot just write or estimate and leave it like that. So 0.6, you need to provide some standard error. To provide that standard error, you cannot, if you don't know the distribution of the or you cannot find the mean square. If I ask any of you now, like find the mean square error of the Pearson's product moment correlation coefficient, that will be a bit difficult for you. Because there may be no, there are some approximation to it which you can use, like the Fisher transform and so forth. But it will be difficult for you to tell me often what is the mean square error. I mean the formula. So we can do so straight away through bootstrapping. What we'll do is that those 10 data sets that I will resample it. In other words, if I select one, I put it back, I select another one, I put it back in the sample, I select, and so I'll do so until I get a 10 observation. Then I repeat this a whole number of times. Each time I'll compute what the correlation coefficient between height and weight. So at the end of the day, I will have what 1,000 correlation coefficients, right? And those correlation coefficients, I will now find the standard deviation, and that becomes my standard error. So then my point says I can now say the standard error of this estimator is maybe 0.2, and then I can find what so it's plus or minus maybe 0.4 to is 0.6, so plus or minus 0.42 or 0.6 and so forth. So that's the idea of this, of how to find some of these things. Okay, so we get back to our um, estimation. Okay, now remember that we went to what fit this, right? So for us to be able to find the fit this, we need what? We need this. Okay, so we copy this, we paste it. Okay, so my data now is what? It's ESV. Okay, the density function that I want to use is exponential. So I put in here ESV. Remember exponential. So, yeah, so It's like exponential. So you can come here and copy so that you don't make any mistake at all. Okay. So you just copy. Of course, this is a character, so it must be in this. Okay. Now start values. As I said, you need some start values. Okay. But you can also leave it blank. R will just, you know, um, can compute it because it will give it its own start value. So there it is. Okay. So remember that our rate was 0.5, but this is 0.429. Okay. Sometimes you can also fit ESP. Okay. So we do it like that. Okay. And then you can do summary. Yeah. So remember our distance was 20. Okay. So you see, these are the sort of things we will get in total with what we have done. So it has an estimate, a standard error or standard deviation, okay, of that estimator. Okay, and then the variance covariance matrix N is and then the log likelihood. Okay, so if I want any of these, I can get it. Remember, in some cases, we will be interested in finding the AIC, the information criteria. So in that case, you will need the log likelihood, right? And so forth. Yeah, so log likelihood is in the stats package. So log likelihood of what? My fit, the model that I have fitted. So if I do this, yeah, so okay, so I should just find this. Yeah, so like this. So if I want my log likelihood, so instead of the function, let's just use a dollar sign. If I want this, so it gives me the the value of my log likelihood. Okay, and yeah, so this is negative, and so forth. If I want another thing like the variance covariance matrix, okay, but this one is just one, right? It's just one estimator. So you just get one. If we do normal, we'll get a 2x2 matrix. If the estimator has 3 parameters, we'll get a 3x3 variance covariance matrix and so forth. All those things you can see it over here, right? Say object. So it means that if you fit the distribution, these are the values that comes up or that you get. Okay, so estimate is the parameter estimates. Okay, so that's what we saw, which is 0.42, 0.42 or 9. SD is the estimated standard errors. V curve is the estimated variance covariance matrix and the log likelihood. Okay, function and so forth. So that's basically that's what we mean by that. Okay, now if I want to see how the role of the sample size in this. Why is it that when we are doing anything, we say do more or take more samples? Okay, it's because the more we take, the more samples we take, the less our errors become. Okay, so I did 20. Let me move it to let's say 50, and then we see what will happen. So 50. Then I fit my distribution. Okay, and then I do let me do it like this. Okay, so you see now it's 0.44. It's getting closer to what? To the the parameter. Let me increase it to 100. And even if you look at the standard, you see it's becoming smaller. Okay. Remember, usually your standard error is a reciprocal of the sample size, right? So you see the first one, we got to 0.4 to the standard error was 0.096. If we go here, it's 0.44. It's closer to the parameter. Also, the standard error is small. So let's look at this again. 100, we put it to 100. We do this. So let me just put it in double parentheses so that I get the values straight away. Okay. So now it's gone up. Even though it's 100, it's 0.44, but we must check it with this. But it's not so 0.44 to 0.5. Okay, 0.445, and this is 0.444. So it's still a bit closer to 8 than that one, albeit slightly. But what happens is that, in practice, if you are doing this, you repeat it over time. So even though we can see our laws of large numbers, we can see the essence of our law of large numbers here. Is not necessarily, how should I put it, like it's not clear cut, okay? So what you need to do is that you should be in a position to repeat this over time. And if you repeat it over time, you'll be able to find your bias and so forth, and you realize that as the sample size increases. Okay, so now I increase it to 1,000. Look at it. It's quite close to it. So almost 0.51, right? And so forth. We can increase this to, let's say, 10,000. And you see 0.495 and so forth. So as you increase the sample size, okay, I've increased it again. You see, you get closer to the parameter value, and also what the standard error also becomes smaller. So that's how this is done. Okay. So what else can we do? Okay. Remember we did a Poisson distribution as well, or the geometric distribution, right? Okay. So let's look at one discrete distribution. So what we did was a continuous. So discrete distribution. Okay. So the geometry, algebra. So let's look at geometric distribution. So the geometric distribution is called a geom, and you have the D for the density, P for the distribution function, Q for the quantile function, and so forth. So remember your work on the previous assignment that you need to get. You see, you have your quantile function like this. This is what you need to do. Okay. So for the what do I mean for the okay, so let me continue, then when I finish we can also define or discuss the quantile function. Now let's see. So here I can also simulate observations as this. Okay, I need n, I need a probability. So the probability can be a vector of probabilities, or it may be 1. Okay. Look at this geometric distribution. So this is a case where you can have what 0. Okay, so this one, it includes the case where you may not have you do it once and there's no success and so forth. Okay, so that's it. Okay, so let's look at this one. Maybe I look at this distribution. Ni is geom. My probability is what 4. 1 over 4. Okay. So here we are saying that n is 4, right? N is 20 and prob is 1 over 4. Okay. Now, if so, there we have our values. Okay. So so it's like this one we got our success on the 8th trial, the next one is the 1st trial, the next one 6, 0, and so forth. Okay. Now, if I want to now find this probability, okay, or the prob, okay, it means I can fit my distribution. I can do fit this, okay, R, okay. So my X is what? Is Ni, all right? And then my dense fan is what? Is geometric, right? We can go back and check. So it's geometric, right? Geometric is there. So I can copy this and paste over there. Okay. So if I run this there, it's now what? 0.22. Okay. But of course, this thing is 0.25. Why? This probability is what you want to find. Because remember, if you remember what we discussed over here, there's only one parameter for the geometric distribution. Okay. So here too, we can, so actually 1.25, we can also increase the sample size to like 50.299, which is above what we want. Okay, let me increase it to 500, and so 0.23. So this is coming closer to it, okay? 0.25, and then we have almost 0.24, okay? If I increase it to 1,000, 0.245, okay? I can increase it to 10,000, 0.25. So this is demonstrating the law of large numbers, right? As we increase the sample size, our estimate gets close to what? The population parameter. Okay. And so forth. Okay. Yeah. Now, you see, if I have, let's say, a practical data set, I can also, pass it through it like that. Okay. So one of the data sets, I gave you the SOA data. So let me look for my SOA data, and then we see how statistics. Okay, so SOA. There's also the Secura data. I'll give that one. That's also about insurance. I'll give that one to you to practice later on. Okay, so the SOA data is like this. So I want to use it. I copy. Okay, I copy it, and then I come to R. So I copy this into my clipboard. For those of you who you just copy. So Control A, Control C, I copy all the data set. Of course, I can also read it straight into R. So there's a video on this which you can watch as well. So R.table, read.table, I should say, read.table, and then my file is equal to, I want to read from my clipboard, which is the, so if I copy if you copy anything, it's in clipboard, there's no header, so I leave it like that. Okay, so SOA data. Okay, so now What is the structure of my SOA data? SOA. Okay, so it's a data frame. The V1 is like that. Okay, so which means it's like more or less like a matrix. So if I want, um, I'll just take the V1 out. So what I'm going to say is that I want it to be a vector, not a data frame. So I'll just say SOA. I put this there. I select V1, and now I do this. So now the structure of my data will be what? It's just um, what is it? It's just a vector, right? A numeric vector. Look at the sample size, about 75, almost 76,000 observations. Okay, so we can plot and see how this is. So first of all, plot and see the data, SOA data, it looks like this. Okay, so there it is. Okay, so the SOA data is like this. It's a very huge claim sums. Okay, of course, the paper I sent you, you can read about it, the data about, but a very large claim. So you see unusually large observations over here. Okay, so now we know the exponential distribution. Okay, I want to, let's say, fit the exponential distribution. Okay, so what do? I will say fit this, right? Okay, so my X is what? The SOA data. Okay, dense.fan is what? It's exponential. Dense.fan is exponential distribution. So I do this, and that's it. So that's the rate. What does it tell us about the mean? Of course, if I were to save um, esp.soa, okay, so if I do that's it. Okay, so the mean is what? ESP dot. So if I ASP dot what? The estimate. Okay, so it's quite huge. Okay, so the mean is what? 54,413 dollars. Of course, here too we can even do the histogram. Sorry, if I track back, histogram of the SOE, and the mean is equal to that. So that will give you this. So you see how this data set is. Majority are over here, and you have some few observations. Okay, you see those two observations, large observations. So this data is highly odd, um, right skewed, right? Okay, so those data sets that extend this to here are classified as outliers, or it may be what? Extreme values and so forth. Okay, so if we look at our SOA, we know it's the rate, the standard error attached to the rate and so forth. Okay, now what what do we do, for example? So for example, you remember your RAINS, right? RAINS, RAINS. So the work that you were doing, you needed what? RAINS, right? RAINS, because there's an exponential QQ plot there. How well does an exponential distribution fit this data? Okay, so we will do ESP QQ. There we have it. Okay, so RAINS, let's go and check because it is in reinsurance package. You go to RAINS. Okay, you have all exponential quantile plot. Remember, this is the assignment I've given you. And if you come here, the exponential quantile plot is like this. So even if you don't know, you can come here. That's why I say study those files. So if you are studying them, you know that this is how it is. So here, okay, you XIN is or the ith order statistic. So I'm going to do this and of course, this is just to help you. I'm going to do this, that, and then I'll write a function to do this on our own, okay, and so forth. Okay. Now, what do I do now? Okay. Yeah. So we can plot this on our own, all right, using the function. So there it is. The function is like that. If you look at it, it's like this. So let me just copy that part and 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 do it. Okay. Here, um, maybe the main, I just want it to be um, that. So my data is SOA. Plot is true. Let's see what happens. There it is. Okay. So this is the quantiles of standard exponential. What does it do? It will get quantiles from the exponential distribution, and then it plots this against the standard, or sorry, the order statistics of your estimator, right? And if you look at it, as we are saying, this, if the distribution fits as well, we will get a straight line passing through the origin, right? 45 degrees line. But if you look at this, well, if you fit a line, it will it, it will come somewhere here. Okay, so it will be a straight line passing through that. We can actually fit that um, on it. We can do an AB line, right, with the quantiles of an exponential distribution and do that. Okay, so this doesn't really fit it well. And of course, it won't fit it well because the exponential distribution doesn't have the sort of tail that this data had. Remember those two values? Those are the ones you see over here. So it's like they are distinct from what you will find from an exponential distribution. Is that okay? All right. So if you fit an exponential distribution to this, what it presupposes is that even though you have a fit, it doesn't really fit. It doesn't capture the data well. So if you are the company, the insurance company, and you have to model claims, and this you are using exponential claims, sorry, exponential distribution to do it. What it means is that it is unable to capture these large, unusually large claims. So it means that whatever you are going to do will be somewhere here, and unusually large claims will come, and you are not prepared for it. Okay, so what you are interested in is to be able to find a model that will be able to fit these parts well, because these are the ones you should be wary of in the, or you should be worried about if you are an actuary or in that company and so forth. Okay, so that's one thing. So a quanta plot will help us to know whether we should even proceed to fit a particular distribution to a data set. Okay, all right. Now we look at how this can be done. Remember that this is it. You say the plot is this, right? This is the quantiles from an exponential distribution. Remember, how do you do that quantile? Remember, I did this in class or something, and because even though it's an um, let's see. Okay, so um, remember that for an exponential distribution, if x, oh, what is happening? If x Okay, just a moment. So yeah, I said that if x is exponential with parameter lambda, then we have our f of x is equal to lambda e to the power negative lambda x. Of course, x, you have your x being greater than or equal to 0, right? Okay. Now, okay. So our f of x also is 1 minus e to the power negative lambda x, right? X. Okay. Now, so the quantile function, how do we find the quantile function? It's the reciprocal of f of x. So what this is a probability p, right? Because it's a value between what, 0 and 1, of course 1 inclusive, so it must be like that. Okay. So it means I can just equate this to p. Okay. Now, if I do this and I solve for x, okay, I solve for x, I'm going to get x to be equal to negative 1 over lambda log 1 minus p. Okay. Now, this p, okay, we can, okay, so we can also say that this x is a function of p right now because we assume that this is a constant, so it's only this that will be changing. So p can be 0, 1, 2, 0 up to what 1. So we can write this as quantile p, which is in q of p, which is x of small letter p, and it is negative 1 over lambda log what? 1 minus p. That p, okay, if you go to r, that's what we are using as negative 1 over what? N plus 1. So here we are using the standard exponential. The standard exponential, lambda is 1. Okay, so that's how you look at it. So lambda is equal to 1, then we have negative. So what is going to happen is that here you have lambda is equal to 1, lambda is equal to 1. Okay, so what you have is that your Q of P is equal to negative log what? 1 minus what? P. Okay, that P, you are saying it is what? I over N plus 1. Okay, when I is equal to 1, you have 1 over N plus 1. Of course, it can be N, but because you move I from 1 to N, when you have 1, this will be 0. We don't want 0 over there. So, I mean, conventionally, we add 1 towards the N, and that gives us what you have over there as I over N plus 1. Okay. So, how do I write that function in R? Okay. So, um, my standard ESP, okay, will be a function. It will be a function which takes in what do you take in? It's just or maybe I can write the function to take in the data. So data, and then what again? Yeah, so just the data. That's all. Okay. So I take in the data. I open this data like this. Okay. So my XIN, okay, the XIN I see there is nothing more than sort, okay, sort X, okay, I sort X, okay, and in this case data. So for example, let's say, remember that we had a, see how sort works, no, okay. Remember we had NI, right? this one is 10,000. I want the smallest one. Okay, so um, okay, so let me just use NI, but I just want to illustrate what sort is. Okay, so NI is of this form. Yeah, so now if I sort NI, if I want to sort NI, sort NI, so you see, it lists it from what the smallest to the maximum. Okay, so that's what we need by so if you go to this plot, you realize that this is sorted. So that's the order statistic. So from the minimum to the maximum. So that's what I mean. So we sort, we have our x in. Okay. Then this part, if we will say QP, okay, QP will then be what? Negative log, okay, 1 minus what? And here we are going to say 1, okay, I will just say 1 to length of data, right? 1 to length of data, okay, 1 to length of data. I put all of it in bracket, and then I divide by what? Length plus 1, length of data plus 1. Plus 1. Okay. All right. So that should be it. And then, so now I can plot what? I can plot um, XIN. No, my X, if I want it to be like this, it will be QP. My X is QP. And then my Y is XIN. Okay. And then what again? Yeah, so if I want X lab, okay, so quantiles of, so I can say quantiles of standard S, something like that. And then Y lab, I can say other statistics, other statistics, other statistics. So let's see. Before I run my function, let me just take some data. Data, I usually don't want to use this because data is inbuilt, right? So let me change everything to D, like cap D, so that it's different from the inbuilt data, which is a function. Okay, so let me say my data is let me sample observations from the SOE. SOE X is equal to SOE size is equal to, let's say, 100 and replace false. Okay, so let's do it like that. Okay, so that's my data. Then I sort my data. I do QP. I plot this. There it is. So this one, it's like an exponential distribution fits as well. Okay, I can go back and do that same thing. I sort the data. I do QP. I do that. So you see this one, it doesn't fit it properly and so forth. So this is what I said you should be doing. So what I have done is to mimic ESP, okay, ESPQ. So now if I can track back, okay, so now my function works well, so I can, if you want it to be exactly the same, maybe order statistics of quantiles of standard, it's too long, so I didn't want to. Standard exponential, standard exponential, okay, so forth. Okay. Yeah. So let me And then we have this ESP, which is inbuilt. So we want to check whether it's the same. It's basically the same. So instead of this, I'll do data and do it. So you see, nothing really changes. It's just the same as what you have. So I can do my function like this. Okay. Then, so I have my function is more or less like um, my own function, just to mimic that of what ESP, right? And so forth. So, I mean, you may not necessarily do it like I have done, because we all have different ways of uh, working and so forth. So if I do the plot first, this is, um, sorry, I clicked something. So, okay. So now I have done my function. I do this, I get that one, and then I also pass the data. I get this. So that's one aspect that I said you should be doing. So that's how you do the quantile plot. So if we want to fit a distribution, we can check whichever distribution that we are going to fit. We can check how well it fits it, and so forth, by using the quantile function and so forth to do some of these things. Okay, so back to our estimation. Okay, example. So any data set that we compute, we can find an exponential. So whether it's an exponential distribution or a normal distribution or what have you, we should be in a position to use what to use maximum likelihood to do it. Okay. If it is method of moment, what you need to do is that there can be other packages that you can use to do it. Okay. But that is basic. So for example, we know that the method of moment, if it is, you equate what? The first moment, okay, which is the first non-central moment to it. Okay. Um, so um, the if we have one parameter, it means the moment estimator will be the mean. If we have two parameters, we can find the mean and the variance. Okay, and then we use that one to equate to each of them, and then we solve for it and so forth. So if it is mean, you are good to go. If it is variance, you can also use your this thing to do that. Okay, so that's the concept and so forth. So I'll end this video, and then in the next video, I'm going to talk about how we can write our own function to compute the maximum likelihood estimator.